Welcome everyone to the podcast of Gas Pathways, a new platform dedicated to technology and innovation in the natural gas industry. Today I am joined by Christian Bauer, one of the authors of a new paper on the climate impact of blue hydrogen production. Hi Christian, thanks for being here.
Hello everybody.
So this paper was quite a collaborative effort among a number of authors from various institutions. Perhaps you could start off by telling me who was involved in the report, and then if you could walk me through what the key findings were.
Yes, that's correct. There were many co-authors involved and many institutions as well. So myself and another colleague, who was participating, we work at the Paul Institute in Switzerland. That's a federal research institute. Then people from ETH, so the Technische Hochschule Zürich were involved. Then from Heriot-Watt University in Scotland, from TNO in the Netherlands, from MIT in the US, from some other US institutions, and from Politecnico Milano in Italy. So it's really a broad range of analysts involved and also of expertise they bring, because the analysis we did, it requires knowledge about life cycle assessment, it requires knowledge about carbon capture technologies, it requires knowledge about methane emissions along natural gas supply chains. So it's really a collaborative effort, and I think we managed quite well in the fact that everybody contributed with core expertise.
Mm-hmm. And what were the key findings of the report? So what can you tell me about the climate impact of blue hydrogen?
Yeah, we analyzed, or what we wanted to know basically is whether blue hydrogen, so a combination of natural gas reforming with carbon capture and storage, whether this kind of production technology for hydrogen could qualify as a low carbon production pathway for hydrogen, and under which conditions, because we found out that there's no kind of black and white or very straightforward answer, either yes or no. It's just, or it's rather, it depends on a few factors, and those factors I think one can summarize with one first factor is the methane emissions along the natural gas supply chain, because if they are high, then since methane is a very potent greenhouse gas, if those methane emissions along the supply chain are high, then the overall carbon footprint of this blue hydrogen is also high and not really worth it from the perspective of climate protection. And the second factor is that at the hydrogen production plant, the CO2 capture rate must be really high to achieve the low carbon footprint. And that's also not always the case. So it really depends on how you design your production chain. And it can be done in a way which results in very low carbon hydrogen, but it can also be done in a, let's say, bad way, which doesn't qualify as low carbon hydrogen in the end.
Mm-hmm. Could you illustrate that with some numbers? So you talk about the methane emissions from the natural gas chain. What sort of methane intensity is needed, and also what rate of what rate of carbon capture is needed in order for hydrogen to be qualified as low carbon?
Yeah. Well, regarding the methane emission rates, we are talking here about a few percent points usually. So at different places in the world, literatures or measurements say that the methane emission rates can be between let's say 0.5% on the low end and up to 3, 4, 5, 6, 8% if the natural gas infrastructure is really dysfunctional and there are a lot of holes in the pipes and so on. So that's the kind of order of magnitude we are talking about. But that might not sound as large variation, but since methane is very much acting as a greenhouse gas, so we are talking about here a factor of 30 more effect than CO2. Or if one applies the 20-year time horizon as opposed to the 100 time horizon, then it's a factor of almost 90. So really small emissions of methane, they play a large role in this context. And that's why also such seemingly small variations play a large role. When we talk about CO2 capture rates at the hydrogen production plant, then high capture rates means 90% or more, basically. So you really have to try to get rid of almost all CO2 which is produced when you split methane, and then geologically store it somewhere to remove it. And that's also not current practice everywhere. So I think it really has to make sure that any kind of low carbon hydrogen from natural gas has to fulfill both of these requirements.
And with regards to methane intensity, where geographically are you seeing the lowest intensity?
Well, currently the evidence suggests that countries like Norway or the Netherlands or the UK, they have a very good natural gas sector in that respect. So means low methane emission rates. It might also be due to the fact that most of their production is offshore and there are no kind of shale gas activities involved, which seem to be more problematic in this respect. And yeah, I think those are the top, or let's say, best practice role models in this context. And I think that internationally one can learn from those practices.
But you also in the paper talk about the difficulty with quantifying methane emissions. There's so many different ways, top down, bottom up methods, and it's very difficult to get, a consensus on which methods to use. Could you tell me a bit more about that?
Yes, the difficulty here is that, well, those emissions, they are not coming from a point source, from one single point source where you could measure them very precisely over a long time. So to get a very good idea on the quantity of those emissions without major uncertainties. It's the opposite. I mean, those emissions, they can or they do occur at the natural gas well, at the pipeline when you transport the natural gas, at some intermediate storages, at the valves connecting those components. So those emissions are very much dispersed in space, and also they show a large variability from a temporal perspective. So you could have events where you emit substantial quantities within a short time, so kind of accidentally. And if you measure just at that point in time, then you measure a high emission. But if you measure at another point in time, then you don't kind of see these emissions. So that's difficult. And so there's the approach you mentioned, both approaches, top-down and bottom-up. Top-down means that you really measure methane emissions at the component level and then extrapolate them to the whole natural gas supply chain, while the top-down approach uses remote sensing, be it from aircrafts or satellites, and measures methane concentrations in the atmosphere. And then researchers aim at assigning those methane concentrations to specific emission sources. And of course, that's associated with uncertainties because in the end, you don't know exactly from which emission source some methane concentration in the atmosphere originates. So there are other emission sources for methane, be it natural, for example, wetlands, or waste decomposition. Then there's the oil sector, which also has some methane emissions. So that's the difficulty here, and I think both approaches come with shortcomings, and it's widely acknowledged that the uncertainties here for those methane emission rates, they are large, and that further research is required to reduce the uncertainties.
Mm-hmm. So what you've been saying is that blue hydrogen can be classified as low carbon, but it depends a lot on how much carbon are you capturing, how much methane is escaping into the atmosphere from the gas chain. I wondered if I could get your perspective on the recent study by Cornell and Stanford University, which casts a lot of doubt on the positive role blue hydrogen could play in the energy transition. Their conclusion was essentially it can't, but it should be cast out and rejected as a tool for decarbonizing energy. What's your perspective on that?
Well, on the one hand, I think I personally appreciate the fact that this study generated some attention for a very important topic, I think, because the question whether blue hydrogen can and should have a role in a low carbon world is an important one. And at the same time, I also think that there is a potential danger of greenwashing from the industry in this respect. So they might try to sell any kind of so-called blue hydrogen as low carbon hydrogen without making sure that the CO2 emissions or the methane emissions are really low. And I think that deserves some attention, and also development of proper regulation frameworks. So from that perspective, I think this study from Cornell and Stanford can be appreciated. On the other hand, I think the authors present some kind of biased study in the sense that they perform the analysis with a parameter setting which is not really representative of best practices, and therefore doesn't do justice to the potential of blue hydrogen. So if they conclude that there is no role of blue hydrogen in a decarbonized world, then, well, based on the parameter setting and assumptions they take, that's true, but I don't think that's the whole story. And that was basically our goal, to explore the space in terms of what could be the potential for blue hydrogen and how low can you get in terms of greenhouse gas footprint, under which conditions, and then see whether those conditions can be met in reality.
Mm-hmm. And you also note in the paper that, well, you describe green hydrogen as low carbon as well, not zero carbon. It is often in a lot of places referred to as zero carbon hydrogen. I could just wonder why you're careful to state that it's low carbon. What is the emissions story there?
Well, the story with green hydrogen is a bit like with battery electric vehicles at the beginning, right? I mean, they had these slogans, zero carbon emissions everywhere, but of course, if one realizes that electricity has to be generated to charge batteries, and this electricity is associated with greenhouse gas emissions, it's similar for an electrolyzer, right? For splitting water and generating green hydrogen. Also, this electrolyzer needs electricity, and this electricity is associated with this electricity production is associated with greenhouse gas emissions. Of course, within the renewable generation technologies, so if we talk about hydropower or wind power or photovoltaic power, there's also a diversity in terms of greenhouse gas emissions associated to this electricity production. So that's why there's also not a single number for green hydrogen carbon footprints. It simply depends on, or mainly depends on, the carbon intensity of the electricity used for the electrolysis. And if we for example, talk about hydropower to be used for electrolysis, that's almost close to zero carbon emissions. So you would get really hydrogen with a very, very low carbon footprint. So way below those numbers which you can achieve with blue hydrogen. But on the other hand, if we think about, for example, photovoltaic electricity generation used for electrolysis, then you do have some non-negligible greenhouse gas emissions from this electricity production, and then you get in a similar range which blue hydrogen production performed according to best practices can achieve.
Okay, and what are based on this paper, what is your advice to policy makers when they're approaching hydrogen?
Well, I think the first and probably most important recommendation for policy would be to come up with policies and regulations in the context of low carbon hydrogen production, which really make it mandatory to follow a life cycle approach, which means that both the infrastructure related emissions, so those associated with the production of the electricity generation technologies must be considered, but as well the methane emissions from the natural gas supply chain. So those are the core elements for green and blue hydrogen. And if those would be ignored or not be taken into account, then such regulations wouldn't make any sense from my perspective, because then you regulate something in a way which doesn't really capture the important elements, and I think that must be avoided at any cost.
Okay, any closing remarks?
Well, maybe as a second lesson or recommendation for policy.
Go ahead. Yeah.
My personal opinion is that hydrogen will play an important role in the future in a decarbonized economy, be it as a feedstock in industry or also as a precursor of synthetic hydrocarbons, which will be needed in aviation, for example. And I think if this becomes true, so if hydrogen gets this important role, then we will need massive amounts of that. And if we need massive amounts and quickly to comply with stringent carbon or climate policies, then I think there's no way of excluding either green or blue hydrogen from support schemes, because support schemes will be needed, because the costs are definitely, currently at least, not competitive if CO2 prices are not high enough, and currently they are not high enough. So I think there has to be done something from the policy side to make this transition happen, and I think that's something which shouldn't wait any longer.
Well, thank you very much, Christian. Good discussion, and thank you everyone for tuning in to another podcast of Gas Pathways, a new platform dedicated to technology and innovation in the natural gas industry. Thank you, and see you next time.